it's a real pleasure to be here and set the scene and give a little bit of overview in preparation for the ASKAP session. And I'm going to give this overview on behalf of the three survey teams from ASKAP who work on extragalactic H1, Wallaby, Dingo, and Flash. Okay, so just a little bit of background first. So why do we want to study neutral hydrogen, H1? How does it fit into our view of galaxy formation and evolution? And on the right-hand side here, you can see some H1 and optical images of individual galaxies. These are very nearby galaxies from the THINGS survey. So what you're seeing is star formation there in purple, the old stellar population in orange, and the neutral hydrogen traced out in the spiral arms here in blue. So what you can see is in these galaxies, and indeed it's a general feature, that the neutral hydrogen extends well beyond the limits of the optical galaxy that you can see in starlight. And so that, among other things, makes H1 a very powerful tracer of the mass distribution in the outer parts of galaxies. And that was indeed these kinds of observations of the outer rotation curves of neutral gas that gave us our first hint that galaxies are often full of dark matter. So that looks like a very elegant picture, but I think what we also know, as you see in the diagram on the left, is that galaxies get disturbed, they interact, and they exchange gas with their surroundings, and they also exchange gas between one phase and another. So we're dealing here with a multi-phase interstellar and often intergalactic medium. And so if we want to have a complete picture of galaxy evolution, how galaxies change over cosmic time, we really need this information about the neutral gas phase, which is really, in many ways, the raw material from which new star formation generations can form. And it's also a very useful dynamical tracer of things that have happened in the history of the galaxy. So if we think about the things that we don't know here, if you look at the classical plot on the left, the cosmic star formation history, we've got a pretty good idea that since redshift 2, this has been declining fairly rapidly. If we look on the right at what the neutral hydrogen has done over the same epoch, we have a much murkier picture. And we really have rather poor constraints between redshift just above 0 and redshift of about 1.5. We don't really have a clear idea of even the amount of neutral gas in the universe, let alone how it's distributed with respect to the galaxy population that we have been studying. So the sorts of key questions we're interested in here: how does the amount and distribution of H1 in galaxies change with redshift? How does this link to the cosmic star formation rate? And what effect does the environment have? What forces act to either have infall of neutral gas into galaxies or to remove gas? And so the instrument that we use to make progress here is ASKAP, the Australian SK Pathfinder, as you see here. It's located on Wadjuri land in Western Australia, and the tool is the 21 centimeter spectral line, the single emission line of neutral hydrogen. So at low redshift, this is fairly straightforward. We have a protected part of the radio frequency band where we can see this line. But as we go into the distant universe, this line is redshifted out of the protected band and into a part of the radio spectrum where there are many terrestrial transmissions, aircraft, mobile phones, radar, all sorts of things. And so for most observatories in the world, there's a large range of redshift which is closed to H1 studies. Because ASKAP is on a radio quiet site, it really opens up a whole epoch of cosmic time for detailed studies of H1. So really what I'm showing here is where the point we've reached now, and what's really for many of us been a 10-year journey to get this telescope built and commissioned and bring it into service to address the science case. So we have 8 ASKAP surveys. The 3 I'm going to talk about, 4 are spectral line surveys. So Wallaby, Dingo, and Flash are extragalactic H1 studies. There are also some transient and continuum studies. And the way that these 3 surveys fit together is shown in this diagram on the left, which really comes out of the original proposal, which Lisa submitted for funding for Astro 3D back in 2016. So Wallaby in green here is looking at the nearby universe, the emission line of H1 in galaxies out to redshift a bit above 0.2. Then you have Dingo, which is extending again in emission, but also with the addition of stacking going out to redshift 0.4. And finally Flash, which uses H1 absorption, going all the way out to redshift 1, which is just set by the frequency limit of the ASKAP receivers. So where are we now? For at least a year now, we've had ASKAP operating at full sensitivity with all its antennas. We've carried out a 100-hour pilot survey for each of these 3 projects. The data has been processed. We're going to see some results here. And we're starting the main 5-year survey program early next year. So under personnel, just mentioned that we have half a dozen researchers funded by Astro 3D, which is enormously beneficial to the project. For Wallaby, Beeching 4 and Tristan Reynolds are both presenting in this session. Dingo, Zhongwan Ri and Sambit Rao Chaudhry. And for Flash Hain Yoon, who'll also be talking here. And the final member of the team arriving, we hope, later this year is Aditya, who's just waiting on travel from India. So just a quick overview of Wallaby. It's an all sky survey covering 30,000 square degrees of sky, 3/4 of the sky, all the way up to redshift 0.2. And science goals include H1 mass function, the census of gas-rich galaxies, environment effects, angular momentum, and so on. Nice survey description paper published last year, and also a very informative public website. I will just lay out for you the location of the early science and pilot survey fields for Wallaby. Here you can see that they're covering fairly substantial chunks of the sky, and I will leave further details for the later talks by Beeching 4 and then the sprint talk of Tristan Reynolds. I will go into a little bit more detail about Dingo because we won't have a dedicated Dingo talk in this session. So Dingo is a deeper ASKAP H1 survey, still with the emission line signal, but going all the way out to redshift 0.4, looking at the cosmic mass density of H1, the H1 mass function, the impact of environment again, and also a whole range of scaling relations and how they vary with redshift. And just showing you here on the right, the range in redshift covered by Dingo, which is rather poorly constrained at the moment by current measurements. And one of the ironic features of this field is that we actually have more information about neutral hydrogen at redshifts above 2 through quasar absorption lines and Lyman alpha absorbers than we have at the moment below redshift 1. So there's a chance to really make an impact here. So Dingo has 2 deep fields, I think, and an ultra deep field as well, covering a substantial area of sky. You can see on the right here just some simulations of the kinds of detections they might expect to make. So really coming on to some of the first results from the phase 1 pilot data. So this is reasonably new data. On the right here, you can see some of the individual galaxies that were detected here. We're going now up to around just redshift 0.1, but achieving the target signal. And you see on the left that the noise is coming down nicely as the integration time increases in the way that you'd expect. So that's a really important proof of feasibility for this survey. So you see there's a number of different kinds of galaxies. Again, the H1 going well beyond the optical galaxy. And in the middle panel on the left, you can see something that looks like a polar ring or disk, possibly a sign of a gas accretion from outside. Okay, I'll just speed up a little bit here. This is a second field, the gamma 15-hour field. And again, processing has been completed. You see some beautiful data here combining H1 and optical information. An important part of Dingo science is actually using stacking to build up sensitivity. So just to combine the H1 signals from groups of optical galaxies, blue galaxies, red galaxies, and so on. So Zhongwan has led a nice paper here that's just about to be submitted. And here, just showing a range of the different kinds of science that you can do, both with direct detections and with stacking. So H1 stellar mass relation, gas scaling relations, and so on, really a wealth of detail here. And now some phase 1 science results from Sambit Roy Chowdhury. He's been looking at the H1 content of pairs of galaxies, groups of galaxies, and isolated galaxies, again with a stacking technique, comparing that with what was seen in the alfalfa survey with Arecibo. So the two key plots are the ones in pink here, just comparing the H1 content of galaxies that are isolated against galaxies that are in groups and pairs. Alfalfa group found that there was, high gas fraction in group galaxies and isolated galaxies. That's not borne out by the Dingo data, which shows that, in fact, the gas content is rather similar in galaxies of different environments. So summary of Dingo, data are processed and ready to go. I will rush very quickly through Flash because we're going to have a nice talk from Hayne on this in a moment or two. Again, an all sky survey. You can see the footprint of the pilot fields on the right, and just a bit of a teaser on the left of one of our detections in the gamma 9-hour field. This is very, very high optical depth line, almost 100% optical depth there, which is remarkable. We haven't seen this in earlier targeted surveys, so this looks like a new population that's just emerging here. And in the last couple of minutes, I wanted to say a word or two about the Australian SK Regional Centre, AusSRC, and just show a couple of slides that I've got from Karen Lee Waddell, who's the director now of this centre. Karen will also be known to many of you as the Wallaby project scientist. So what happens with the data? This is showing the data flow for Wallaby, but in fact for Dingo and Flash, it's rather similar. Observatory processed data on the left, that gets released into the CASDA database. And then post-processing is really what's needed to get the maximum science value. And that's what will happen now in collaboration with the new regional centre. This is really ramping up expertise to be able to conduct science with SKA and to train people to develop algorithms and so on. Good news is there's $63 million of funding from the government to actually set this up and have it operate from next year right up to the time when SKA becomes operational. And the early focus for the next 5 years will be on developing functionality that's of benefit also to the ASKAP and MWA survey teams. So a lot of extra effort to go into extracting maximum value from the ASKAP data. This is just a little schematic of some of the things that will happen here, software and tools, connecting databases and so on, and actually providing value-added databases to the user community. So this is really good news. And we're looking forward, I think all of us in the ASKAP teams, to working with Karen and her software team on these tools. And I'll just put my summary slide up here because I think I'm almost out of time, Chandra. But the good news is we're having data now coming from the full telescope. We've got the pipelines and the post-processing resources in place. And I think there are many opportunities now to take this H1 data and not only study in its own right, but also have cross-project collaborations with Astro 3D, both with the simulations and with a number of the galaxy evolution and semi-hector surveys. So I'll stop there. Thanks very much.
All right, thank you so much, Elaine, for that nice overview talk. So we already have a question on the Slack channel by Katie, who asks, will ASKAP allow us to obtain valuable kinematical information from models of gas accretion and jet-driven feedback in radio-loud galaxies and its evolution over redshift?
Yes, I hope so. Certainly one of the threads of what we're doing is we can see associated H1 absorption in galaxies where there's black hole accretion happening. And the example that I showed from Flash early on, and Hayne will show some more, is one example of that. So we don't know yet whether this is something that's evolving with redshift, but what we are seeing is that the H1 that we're seeing in absorption is not necessarily in the kinds of active galaxies that we would have expected to be very gas rich. It seems to be turning up also in quite low excitation radio galaxies with a lower accretion rate. So I think there's really a lot to learn here. And we really value our collaboration with the Genesis team. We've been quite active working with them to try and bring the models and the data together. So I hope that answers Katie's question.
Right, thanks, Elaine.